So we are going to start with moles today. Okay. So basically, mole is a physical quantity. You can compare it with the 1 dozen, for example. For normal things, we use 1 dozen, and when we say 1 dozen, it means that there are 12 pieces or 12 items of that thing, right?
Yes.
Okay. So in the same way, if I am saying 1 mole, then it means these number of particles must be there. And if I write it in a normal way, 15, 18, 19, 20. So it could be around like this. So if we have these much pieces or these much items of anything, then it is considered as 1 mole. Is this understandable?
Yes, sir.
Okay. So we call this figure 6.02 exponent 23 a Avogadro's number, or it is also called Avogadro's constant. Okay, when we say the number, it is equal, it is the particles number which are present in 1 mole. So the particles are of three types. They can be atoms, they can be ions, and they can be molecules. Is this understandable?
Yes, sir.
Okay. Second important thing that you have to remember is that the mass of 1 mole is equals to its AR or MR in grams. Okay. That, for example, here we have few examples. I will give for few more examples to make this concept clear. For example, if we say, if you look in the periodic table, here we have, see, the relative atomic mass of sodium is 23, right?
Yes.
Do I use any unit with this 23?
Mm,
Sorry?
no.
No, because it's a relative atomic mass, and when we relate it, the unit would be cancelled out. But if instead of 23, if I say I have a 23 grams of sodium, so if I'm putting the unit gram over here, so do you think it can be a mass of a one atom only?
No, it's a quantity of
It's a quantity.
sodium.
Sorry.
It's a quantity of sodium.
Yeah, it is a big quantity of oxygen of sodium. So how many sodium it means? If I'm using this, then it means it is 1 mole of sodium. And if I'm saying 1 mole of sodium, then how many atoms would be there? Because it's atoms, so it's 6.02 exponent 23 atoms of sodium would be there. Did you understand this part?
Yes, sir.
For example, the relative atomic mass of hydrogen is 1, so we don't use one unit with 1. But if I say 1 gram of hydrogen, then it means now I'm talking about 1 mole of hydrogen. And if I'm talking about 1 mole of hydrogen, then it means 6.02 exponent 23 atoms of hydrogen. In the same way, if you look at titanium, its relative AR is 47.9. But if instead of 47.9, I have mentioned so for 47.9 grams of titanium, then it means it is 1 mole of titanium. And if it's 1 mole of titanium, then it's 6.02 exponent 23 atoms of titanium. This point is clear?
Yes, sir.
Okay. Now, there is another example. For example, if you look on water, what is the relative molecular mass of water?
18.
18. With no unit, right? It's just 18, right? So it means it is
Yes.
one mass of one molecule. Is it understandable?
Yes.
Okay.
Yes, sir.
So it is a mass of one molecule. But if instead of 18 gram, if I say if instead of just 18, if I say 18 gram of water, so it means now I'm talking about 1 mole of water molecules. And now water is basically a molecule. So now it has 6.02 exponent 23 molecules in it. Is this understandable?
Yes, sir.
Okay. Now, here we have few formulas of a mole conversions that you must remember. That mole, if I have provided with the mass and I have to convert it into moles, then I will divide that mass with its AR or MR. If I am given with the number of particles, I divide with the Avogadro's constant or Avogadro's number, that is 6.02 exponent 23, I will get the moles. If I am provided with the volume of a gas, if that volume is in decimeter cube, so I divide it with 24 decimeter cube, I will get the number of moles. If I get the volume of a gas in centimeter cube, I divide it with 24,000 centimeter cube, then I will get 1 mole. Okay. So, and all
Yes,
of
sir.
this, that 24 decimeter cube or 24,000 centimeter cube is used at RTP, room temperature pressure conditions, which are these. Till here, is this understandable?
Yes, sir.
And secondly, sometimes students do this mistake that the volume of a liquid of a aqueous solution is given and they are using this formula. So remember, this formula is used only for gases, okay?
Yes, sir.
Okay. Now, next we have a moles. When moles is equals to, if we are given with the concentration and volume of a solution, so if we multiply that concentration with the volume, I will get the number of moles. And to convert the volume into decimeter cube, what do you usually do? Normally, they provide you the volume in centimeter cube, so we divide it with 1,000
Divide by 1,000.
it into decimeter cube. Okay. Now, there is one more formula to find the percentage by mass of any element. For example, if I have ammonium nitrate. So how many nitrogen it has?
2.
2. So to find the percentage of nitrogen, I'm going to put the mass of 2 nitrogens in the numerator, and I'm going to put the MR of the whole compound in the denominator, and then we multiply it with 100 to get the percentage of nitrogen. Is this understandable?
Yes, sir.
Okay. Now, here we have a unit convergence. For example, if you are given with the centimeter cube, volume in centimeter cube, you divide it with the 1,000, you will get decimeter cube. If you have a decimeter cube, you multiply it with 1,000, you will get the volume in centimeter cube. If you have a volume in centimeter cube, you divide it with exponent 6, you will get the meter cube. Okay.
Okay.
And if you have a meter cube, you multiply it with exponent 6, you will get the centimeter cube. In the same way, if dm cube is divided by 1,000, you will get meter cube, and meter cube is multiplied by 1,000, you will get decimeter cube. Is this clear?
Yes, sir.
Okay, you have to know these conversation, and then the temperature conversation. If you have a temperature in Celsius, you add 273 in it, you will get the reading in the Kelvin scale. And if you have a reading in the Kelvin scale, you subtract 273 from it, you will get in degrees Celsius. Is this clear?
Yes, sir.
Okay, now we have new thing that is basically the application of the previous moles convergence formulas, and it is called stoichiometric calculation. It is, for example, we have this case, a nitrogen is reacting with 3 moles of hydrogen and we are getting 2 moles of ammonia, right?
Mm.
So, for example, if examiner provides you that 35 grams of nitrogen is used and they are asking the volume of ammonia gas produced. So whenever you have a chemical reaction and examiner gives you the equation, examiner tell you the reaction and provide you information about either any one of the reactant or a product from that reaction and ask you the amount of any other substance from the chemical equation, these kinds of calculations are called stoichiometric calculations. Is this clear?
Yes, sir.
So in these kind of calculations, we usually use this route. For example, they have provided you the amount of any substance, right? That is considered as given. So what you need to do, you would need to convert that amount into moles. If it's moles, then it is fine. Otherwise, if it's the number of particles, you divide it with the Avogadro's number to convert it into moles. If it's mass, you divide it with the AR or MR to convert it into moles. If it's a volume of gas, you divide it with 24 decimeter cube or 24,000 centimeter cube to convert it into moles. If it's a volume and a concentration of a solution, you multiply both of them by, and remember, keep the volume in decimeter cube to convert that concentration and volume into moles. Is this clear?
Yes, sir.
Okay. So then you will make the ratio, and in this ratio, there is one other thing. This ratio is always taken from balanced equation. So we got one ratio from the balanced equation, and then we put the moles of the given substance over here and put the moles of the other substance as X, and then cross multiply to get the moles of the other substance, which one is required. Is this clear?
Yes, sir.
And then whatever the amount is required, we again use that specific expression I have mentioned over here to convert that amount, that moles into that specific amount. Any questions still here?
No, sir.
Okay. Then we have a percentage yield question sometimes. So what we do in percentage yield question, there are two types of yield. Yield means product, that how much product is formed. So the from the calculation, whatever amount we calculate is calculated yield or theoretical yield. And when we actually perform the experiment and the amount of product we got is called practical yield. Okay.
Mhm.
So what will we do? That most of the time examiner provides you this practical yield, and examiner asks you to calculate the percentage yield. So calculated yield, practical yield is given, which is actually obtained from the experiment. And the calculated yield can be obtained by this method, the above method, by taking the ratio of the given substance and the unknown substance whose percentage yield needs to be calculated. Then after calculating it, we put it in the denominator. The practical yield must be in the numerator and then multiply by 100 to get the percentage yield. Is this clear?
Yes, sir.
Okay. And then limiting reactant. So the one which is in lesser amount, and I think I must add one more point over here, that and used up first. Other one is the excess reactant which always left behind. So in the yesterday's case, if you recall, we are burning hydrocarbon with the oxygen, right?
Oxygen is in excess
And
amount.
oxygen is in
Yes.
excess. So it means that oxygen is in excess. So some of the oxygen is left behind after the experiment, right?
Yes.
So it means that the organic compound is limiting reactant over there, because during the reaction, it was completely used up. We are not getting any volume or any amount of that uh, organic compound
Yes.
at the end of the experiment, right?
Yes, sir.
So that is the limiting reactant. Any questions so far?
No.
Okay. Now, there is one more uh, expression that usually asked by the examiner. That is this expression, the numericals comes from this expression as well. This is called ideal gas expression. And here we have uh, this is PV is equals to nRT. So for example, if you have to calculate if they give you out of these five things, if they give you any four things and ask you to find the other thing, then you will use this expression. And normally this expression is used in non-standard or non-standard conditions. If these conditions are not there, then we will use this expression. Okay. So now
Mhm.
here you have to keep in mind few things. P is pressure, which is always kept in pascals. So if examiner gives you the pressure in the kilopascal, you just multiply by 1,000 to turn into pascal. Okay. Volume must be in meter cube. So that's why I have told you these conversions over here. If the volume is in centimeter cube, then that's how you will convert it into meter cube. If the volume is in decimeter cube, that's how you will convert it into a meter cube. Okay. Then
Okay.
N is the number of moles of gas. R is ideal gas constant. It is always given at the end of the exam paper. You have two papers. One is a constant values that the examiner provide you at the second last page, and at the last page, examiner provide you the periodic table. Okay. So there is no need to remember it if okay, so it is always provided over here. Then temperature is K. This must be in Kelvin. So if we have a temperature in degrees Celsius, we add 273 in it to convert it into K. Okay. So what was N? N is the number of moles, right?
Yes.
So if I changes that number of moles, we know that number of moles are equals to mass upon MR, right?
Yes.
So I opened the number of moles, I substituted mass upon MR instead of number of moles N. So if I do so, and I move MR over here and these two over here, so I got one more expression to calculate the relative molecular mass of a gas, right?
Yes, sir.
So sometimes see in the previous questions where you were working, you were doing, the MR is given and they are asking you to find the molecular formula after calculating the empirical formula, right?
Yes.
So in some questions, what examiner do? Examiner allow you to calculate the empirical formula, then examiner provide you the information to calculate the MR, and sometimes you need to use this expression to calculate the MR, and then they ask you to calculate the molecular formula. Okay. Any confusion still here?
No, sir.
So shall I give you a question to do? You can try
Yes.
first, or I will help you to do it.
I can try it.
You want to try first?
Yes, sir.
Okay. Okay. Now, first, can you try A and B and send me the WhatsApp? Okay, try the whole A and B. Yeah.
Sir, I don't remember the exact definition of the catalyst.
Okay. So what you remember? Tell me.
Uh, it is a substance that helps the reaction go faster.
Yeah, yeah. That speeds up the reaction by lowering the activation energy. Okay.
Yes, sir.
Thank you. Okay. So you continue your work. Okay.
Yes, sir.
So what is meant by the term catalyst? A substance speeds up chemical reaction by providing alternate route. Either you can write that of a lower activation energy or by providing alternate route of lower activation energy. Both are correct. Okay.
Okay.
Okay. What equation you made in VA1?
H2O2
H2.
equals to O2 plus H2.
H2O plus O2, very good. See, they have mentioned over here that catalytically decomposed to give water and oxygen. So this is the reactant and these are the products. Okay, how we will balance this equation, Kalishma?
Mm, We could put 1.5 in front of O2.
Yeah, we can put 1.5 in front of O2, or it can be balanced by this way as well. H2O2 gives you 2H2O plus O2.
Okay, yes.
Is this fine?
Yes, sir.
Okay. So did you figure out to which homologous series this C15H32 belongs?
Alkane.
Alkane, right? Because it's, if you see the general formula is Cn, very good, Alishma. CnH2n plus 2. So C15H2 times 15 plus 2 gives me 32, right?
Yes.
So it's C15H32. Now, use the equation above. It means they are talking about this equation. And your answer to A2, it means they are talking about this equation. So you have to use these two equations to calculate the amount in moles of H2O2 that will provide sufficient oxygen for the complete oxidation of 1 mole of C15H32. Can you do this? How you will do this?
So 1 mole of C15H32. We
Yes.
require 23 moles of oxygen.
Very good. So we got one ratio over here. Very good, Alishba. That C50, 1 mole of C15H32 needs 23 moles of oxygen. Now,
And to get 1 mole of oxygen, we need 2 moles of H2O2.
very good. You correctly identified the ratio that for 1 mole of oxygen, 2 moles of H2O2 are required. Yeah. Next.
We would cross multiply these both.
No, not these four. See, now, if you read it carefully, what they are saying that you have to calculate the amount of moles of H2O2. So it means I need the moles of H2O2, which would be X.
And O2 would be 23.
Yeah, O2 will be 23 because they are asking it the moles of H2O2, which provides sufficient oxygen for the complete oxidation of 1 mole of C15H32. So we have figured out that for 1 mole of H2 C15H32, 23 moles of oxygen are needed. So we have to figure out for that 23 moles of oxygen, how much H2O2 is going to produce it. Understood?
Yes, sir.
Now we will cross multiply it. So here, this is a little difficult question related to the rest of the one because here you have to make the ratio from the two equations. Most of the time examiner asks you the question in which only one equation is used, so the ratio can be made easily, but here this one is a little tricky. So if I calculate the
So
value of X, it is going to be 20.
it's 46.
Very good. So we are getting 46 moles. So the moles of H2O2 are 46. Is this clear?
Yes, sir.
Okay. Now have a look at next part. A submarine equipped with a Walter engine used 212 tons of diesel fuel. Okay. During an water voyage, the submarine also carried concentrated aqueous H2O2. Okay, they have given you the conversion that 1 ton is equals to exponent 6 grams. Calculate the amount in moles of diesel fuel used during underwater voyage. So I have to find the moles, and I am given with the mass in tons. So I'm given with the mass, right?
First, we need to convert the tons into grams.
Very good. So
And
if I need to turns into gram, I can make the ratio that 1
yes,
is equals to exponent 6 grams, right?
yes,
So if I have 212 ton, then how much grams? X grams would be there. So if you calculate it, you are going to get 212 exponent 6 grams, right? Or
yes, sir.
2.12 exponent 8 grams.
Yes.
Okay. Now, which formula we are
Now we would
we use to find the moles?
moles equals to mr over mass over mr.
Mass over MR. So it means I need a MR of a diesel, right?
Yes,
So C15H32. So C15, 12 times 120, 120 and 60. Is it 180
yes,
and plus 32?
it's 212.
212. So the number of moles
Yes,
is equals to 212 over 212 exponent 6. So 212 will be cancelled out and I am left with 1 exponent minus 6 moles. Isn't it?
yes, sir.
No, sorry.
1 exponent.
212 exponent 6, not minus 6, because this is mass and this is MR, not minus 6. Okay. I
Yes,
actually
sir.
put the wrong values initially. So 1 exponent 6 moles. Is this clear?
Yes, sir.
Now use your answer to B2 and C1 to calculate the mass in tons of hydrogen peroxide used during underwater voyage. Okay. So if you see, I can easily relate that for 1 mole of diesel, how much hydrogen peroxide I needed?
46 moles.
46 moles. So I got this ratio. Now I'm going to apply this ratio over here only, that C15H32 is to H2O2.
Hmm.
And for 1 mole of diesel, I need 46 moles of hydrogen peroxide. So if I have 1 exponent 6 moles of diesel, then X moles of H2O2 would be needed. And these X moles of H2O2 would be equal to 46 exponent 6 moles, isn't it?
Yes, sir.
Or I can write 4.6 exponent 7 moles.
7.
Yeah, very good. Now, part D. Can you tell me the answer?
They would react with water.
Okay, what are the products? What are the products?
The products are carbon dioxide and water.
Okay, water just get mixed. So there is no need to talk about water because it's already water, right?
Yes.
In the sea. So what happens with the carbon dioxide?
It
Do you
is
think,
used by plants.
no, do, do you think you said, yeah, it is obviously finally used by aquatic plants in the sea, the marine plants. But initially what happens? You said you use the term reacted, right?
Yes.
It can be correct, but okay, how we make the soft drinks? We dissolve the carbon dioxide in it. So the most appropriate would be that it would dissolve because it's an acidic gas.
Okay. It would dissolve in sea.
Yeah, it would dissolve or it dissolving. Is this clear?
Yes, sir.
Okay. Oh no, sorry. Take the screenshot of this one.
Yes, sir.
And this one as well.
Yes, sir.
Okay. Now this is for you.
Okay.
Okay. Now I want you to see how you can attempt it without my help. So do it. Where you find any help, you can ask. Okay.
Yes, sir.
Okay. Start.
Yes, sir.
So actually, the comprehension of the initial information is very important. Now read the question again carefully. Ammonium sulfate is widely used as a fertilizer. Okay. In order to determine the percentage purity of a sample of ammonium sulfate fertilizer was analyzed by reacting a known amount with an excess of NaOH. So it means that some of the NaOH left behind, right?
Yes.
And then titrating the unreacted NaOH with HCl. So that left behind NaOH is titrated with HCl. Is this clear?
Yes, sir.
Okay. Now ammonium sulfate react with NaOH in 1:2 ratio. Complete the balanced equation for this reaction. You made after this what you made? Can you tell me?
Sir, I made 2 NH3 and
Okay.
then Na2SO4 and then 2 molecules of water.
Na2SO4 and H2O. And if I go to balance it, I'm going to get 2 over here and 2 over here. Very good. Okay. Now, a 5-gram sample of fertilizer containing ammonium sulfate was warmed with 50 centimeter cube of 2 mole per dm cube NaOH. When all the ammonia has been driven off, the solution was cooled. The remaining NaOH was then titrated with 1 mole hydrochloric acid, 1 mole per dm cube hydrochloric acid, and 31.2 centimeter cube were required for the neutralization. Okay, so here we got the concentration of NaOH. Here we got the volume of NaOH, which is in excess, right?
Yes, sir.
And that is the sample containing fertilizer. So it is basically impure ammonium sulfate. Did you understand this part?
Okay.
That 5 gram is not the whole 5 gram is not whole ammonium sulfate. There are some impurities in it. That's why we are going to calculate the purity. Here we have a concentration of HCl and here we have a volume of HCl. Okay, write a balanced equation for a reaction between NaOH and HCl, and I think it's very easy for everyone to write this equation. Is this clear?
Yes, sir.
Okay. Calculate the amount in moles of HCl. Okay, so if I'm going to calculate the amount in moles of HCl, so I'm going to use its concentration. This would be the formula.
Volume.
This is the formula. So concentration is
Yes.
1.20 multiplied by volume, which is 31.2 divided by 1000, right?
Yes, sir.
Can you tell me the answer?
0.0312 moles of HCl.
0.0312. These are the moles of
HCl.
HCl. Okay. These HCl actually, can you tell me with which substance these HCl was reacted?
Sodium oxide.
Sodium
With the
hydroxide.
remaining sodium oxide.
Yeah, that's very important. See, reacted with
Remaining sodium hydroxide.
sodium hydroxide. Okay. Calculate the amount in moles of NaOH. Okay. So these are the moles of NaOH, which are the total moles of NaOH, right?
Yes, sir.
So the concentration is 2.00, volume is 50 divided by 1000. 1.0 exponent 3 or 0.1?
I got 0. Yes, 0.1 mole of
0.1.
sodium hydroxide.
We get 0.1 mole. Okay.
Yes, sir.
Okay. Now what they are saying, use your answer to 1, 2, and 3. Calculate the amount in moles of NaOH used up in this reaction. Okay. These are the total moles of sodium hydroxide, right?
Yes.
Okay.
And
From
you
this,
told us in the beginning that the ratio between ammonium and sodium hydroxide is 1 to
yeah, the ratio between ammonium hydroxide and HCl would be
HCl or sodium hydroxide.
sodium hydroxide and HCl. It is because, see, this 5 gram is not whole ammonium sulfate, right?
Yes.
So if I convert this 5 gram into moles of ammonium sulfate, so do I get the correct moles?
No, because it is impure.
Okay, it is impure. So how many ammonium sulfate would be in this? It would be 5, 4.0, 4.2, 4.5. We don't know, right?
Yes.
But we know the exact moles of HCl, isn't it?
Yes.
And we know the mole ratio of the HCl and NaOH from equation 1. In equation in
Yes.
B1,
Yes.
what is their mole ratio?
Mm. 1:1.
1:1. So it means, can I write over here that moles of NaOH reacted with HCl is equals to 0.03124.
Yes.
So from now, see, from these moles, only this mole of NaOH would reacted with HCl, right?
Yes, sir.
So it means the leftover moles would react with an ammonium sulfate.
Yes.
Got it?
Yes, sir.
So moles of NaOH. So if you connect the links and read it very carefully, it will be relatively easy to attempt it. So moles of NaOH reacted with ammonium sulfate is equals to 0.1 minus 0.03124. Can you tell me the answer?
0.0688.
0.0683.
688. 8.
688. Okay. Now, use your answer to 4 and equation A to calculate amount in moles of ammonium sulfate reacted with NaOH. So if you see equation in A, the ratio of ammonium sulfate with NaOH is 1:2, right?
Yes.
So it means we are going to make that ratio. NaOH 2 moles reacts with 1 mole of ammonium sulfate. So 2:1. So here we got 0.0688 moles of NaOH. So the moles of ammonium sulfate would be X. So if you will calculate the value of X, it is going to be 0.0688 divided by 2, right?
Yes. Which is 0.0344.
0.344 moles.
0.0344.
Sorry. Yeah, 0.0344 moles. Now what they are saying, use your answer to 5 to calculate the mass of ammonium sulfate with reacted with NaOH. So I got the moles, I multiply with MR to get the mass, right?
Yes.
Moles into MR. So 0.344 into, have they given the MR? So
We haven't.
sulfate is 96. Nitrogen is exactly 14, 14 and 4, 18. 18 and 18,
36.
36 plus 96,
132.
132. So just multiply them.
We get 4.5408.
So see, these are the grams of ammonium sulfate which are exactly there in 5 grams of sample.
Which is pure. Like the
So
pure is
this is the
4.5.
pure ammonium sulfate in that 5 grams. So see, if you able to correctly linked all the things, then this part will be the easiest. Otherwise, I have seen that this part would be the worst for a student, how to find the percentage purity. So you know the pure ammonium sulfate, you know the
Yes,
mass of sample, you just multiply with 100 to get the percentage.
it is 90.816.
90.8%.
816.
Okay. So did you understand? Any confusion, any queries?
No, sir.
Okay. So now you will start doing the past papers of atomic structure and moles. And I think
Okay.
if you want, then I will continue moles tomorrow. Otherwise, I will be moving towards the new chapter.
Sir, I'll try to attempt the questions, and if I find difficulty, I'll let you know, and then we can
Yeah,
see
sure.
and
If
do
you
one more
find
step.
any difficulty, then we will continue moles tomorrow. Otherwise, we will be continuing the new chapter, inshallah.
Inshallah. Which
Okay.
will be chemical bonding.
Yeah, inshallah. Chemical bonding.
Okay.
Okay, take care. Goodbye. Allah Hafiz.
Gracias.